Thank you.
Thank you.
So, thank you for attending this talk on my paper, the performance and usability of visual and verbal key verification of word-based key fingerprints. This is a joint work by myself, Helen, Petrie, Siamak, Shahandashti, and Aidan, Fray, all from the University of York. So to start off with, I want to discuss what we mean by a key fingerprint. So a key fingerprint is a short string computed through the cryptographic hashing of the user's key material, and is often included as an optional additional security check in secure messaging applications or end-to-end encrypted messaging applications. They're able to they enable the verification of key authenticity over an out-of-band channel, where an out-of-band channel is a channel that is able to provide message integrity of short messages. In the remote case, this tends to require involvement of the humans in a manual comparison, which does introduce the potential for human error, and provides the adversary with an interesting additional threat vector where they may attempt to fool users into accepting similar fingerprints and being able to implement a person in the middle attack. So now I'd just like to provide some examples of what a key fingerprint may look like. So the first, the bottom image is an example of a key fingerprint in an SSH connection. First, probably the thing that stands out most there is that it's not particularly usable. So a key fingerprint using a manual comparison will be encoded into human readable form. And in terms of SSH, I'm not sure how often they are really compared. And one of the difficulties there is the actual encoding. The top three images demonstrate three examples of key fingerprints used in secure messaging applications. So the one on the left is from Petrie Privacy, which is an extension of the OpenPGP secure messaging for email, and is supported by modern email clients such as Thunderbird, and the image here shows their iOS app. So in this example, the fingerprint consists of the 5 words Iniesta, Belbin, Tove, Ditor, Raymond. And the task for the user would be to compare those words with those of their intended recipient, and if they feel that they are identical, they will confirm them and be assured of the authentication of the keys. And if they feel that any of them are mismatching, they would reject them. In the middle example, there are 2 different representations of key fingerprint. The one at the top is a visual representation, which can be quite challenging in my opinion, as it's quite difficult to observe small differences between 2 images. And beneath is a hexadecimal version of the key fingerprint, which is again probably quite challenging for users to compare, as it's not a representation that they are used to comparing or comparing everyday life. On the right hand side is the version of what the key fingerprint comparison in WhatsApp or Signal. At the top is the QR code, which largely solves the problem in the case where users can meet in person, as they're able to scan the QR code on their own device. But this is unable to be used in the remote case, and they're required to fall back on a comparison of a numerical fingerprint, which is another example of an inch representation used in practice. In our talk, as we'll see soon, our focus is the examples using the fingerprints used in Petrie Privacy. So now I'd like to discuss how remote users exchange key fingerprints over the out-of-band channel. So there's really 2 options, a visual exchange and a verbal exchange. The visual exchange was used in practice historically. That used to be the way that fingerprints would be exchanged in practice. One example was that users would print their PGP fingerprint on a business card and share them at a conference or via post. Another example is they could send the relevant fingerprint via a text message. The other option that is more commonly now encouraged in secure messaging applications is a verbal comparison, where the intended recipients call each other by a phone call and read out either their word-based fingerprint or the numerical encoding of their fingerprint and decide whether they are identical or they are mismatching. So now, in terms of the background, so the usability issues with secure meshing applications have been well known and well studied for a number of years, starting with the seminal paper from Can, Johnny and Cript, and subsequent papers have found similar effects, and also similar effects have been found in modern secure messaging applications such as Signal. In terms of our work, the most relevant studies are those of Helen from 2016 and that of Tani L from 2017, who investigated the performance and usability of a range of different key fingerprint representations. They found that word-based key fingerprints were best and achieved the lowest error rates. Yet both studies only used a visual comparison mode, whilst verbal comparisons are increasingly common in modern applications. And this was something that we were interested in investigating in this work. Additionally, interesting differences have been observed between visual and verbal comparisons in the context of secure device pairing, which gave some motivation for the investigation of the differences in this work. But in the context of secure device pairing, such protocols involve substantially shorter fingerprints and tend to involve only a single user in a local network. So, for example, they may be authenticating a printer on the local network or other IoT device. Alongside differences between comparison mode, we also felt that the participants' own cognitive or learning style may be an important factor in their performance of a key fingerprint verification. I thought that the preference to receive or interpret information is something that we want to measure. There are examples of this in modern day life. For example, my partner much prefers to read, to listen to an audiobook when wanted to listen to a story, where I much prefer to read a physical book, and the differences there, and there are many other examples. So to measure the difference in learning style and preference to receive information, we chose to use the index of learning styles, which has been shown to be a valid and reliable instrument to measure learning style. It has high test-retest correlation scores after periods of between 8 weeks and 4 months. The visual verbal subscale is one of the 4 subscales and enables the assessment of the participant's preference to receive information visually or verbally. The subscale consists of 11 questions with 2 forced choice options in each case. One of the options is a verbal response and the other option is a visual response. In terms of scoring, each time the participant chooses a visual response, they are given a +1 to their score. And each time they choose a verbal response, they're given -1 to their score. And this leads to a score which is an odd number between -11 and +11, which is also shown in the figure at the bottom of the slide. So given this background and sort of ideas behind in the study, our hypotheses were that we sought to investigate. We felt that there is a significant difference in the time to make the correct decision, the number of errors, and the perceived usability ratings between the visual and verbal fingerprint comparisons. Additionally, we felt that participants will perform better and report significantly greater perceived usability when the comparison mode aligns with their preferred method to receive and process information. In terms of the design, we chose to use a within participants design with 2 conditions. Each participant would compare 20 fingerprints visually and a further 20 distinct fingerprints verbally. The order was counterbalanced to enable us to avoid learning effects or mitigate for learning effects. The fingerprints used in the study consisted of 5 words selected from the Trustwords word list, as used by Petrie privacy. So the reason for choosing Petrie privacy is it's an example of a real application that uses a word-based key fingerprint representation, and word-based key fingerprints have been shown to perform well in previous research. Of the 20 comparisons in each condition, 17 of them were Nonattack comparisons, where all words were identical between those received from the intended recipient and displayed on the secure messaging device, as an example of which is shown at the top of the slide. 2 of the attacks were randomly selected to be attack comparisons, with all differences combined to the third and fourth words. The reasoning behind this was that we felt that differences at the start and end of the fingerprint strings would be easier to identify, and this was also a practice followed in previous research. The final comparison was a total mismatching attention check, which we included in an attempt to identify those participants who may be clicking through the study and maybe not behaving as we would have expected. In terms of defendant variables, we were interested in measuring participants' performance and perceived usability. So to measure performance, we measured the time for participants to make correct comparisons and the number of attack and non-attack errors that they made. So an attack error would be when they accepted
I think you froze, Lee.
variables. Were you able to hear what I said about the previous slide, which was this slide?
If I remember correctly, yes.
Okay, so in terms of the dependent variables, we were interested in measuring the performance and perceived usability of the participants. So to measure performance, we measured the time for correct comparisons and the number of attack and non-attack errors made. So an attack error would be when the participant would accept a fingerprint that was non-matching, with some of the words were different, which would enable the adversary to implement a person in the middle attack. A non-attack error would be when the participant would reject two fingerprints that were actually identical, as they believed that there was some form of difference between the received fingerprint and that displayed on their secure meshing application. To measure perceived usability, we measured it using 12 5-level rating items. We did not use the system usability scale, or SUS, as we felt it was old, and there were questions included that were not relevant to our context. So in terms of the 12 questions, they are shown on the slides. We grouped the 12 questions into 6 dimensions, where the scoring of the questions was flipped where necessary, so that a high score was always corresponding to high usability. And we were interested in measuring the perceived efficiency, ease of use, the low mental workload, confidence, whether they would repeat their use of the comparisons, and the trust that they had in the comparison. In terms of participants, we used several methods of recruitment. We recruited participants from the University of York network, from within the author's local contacts, and also using Amazon's Mechanical Turk. Now, the reasoning behind this was that previous work has suggested that, or questioned the quality of data collected from Mechanical Turk. And we wanted to make sure that we were able to mitigate for this threat. However, no differences were detected between the groups in our analysis, and so we present the data as a whole. 75 people responded to the survey, of which data from 62 participants was analysed. Of the the participants whose data was eliminated, 2 identified themselves as dyslexic. We chose to not include this data in our analysis, since the dyslexic participants the experimental condition involved reading and listening to words, and dyslexic participants would likely find this a challenging task and make different kinds of errors. But they do present an interesting additional avenue of research. Now, in terms of materials and tasks, as mentioned, we produced a bespoke web app to enable the participants to interact with mock-ups of 2 devices. The mock-ups of the secure meshing application was based on the pretty easy privacy secure meshing application, for reasons mentioned earlier in the presentation. On the left-hand side, the visual condition demonstrates the visual condition in which the participant will be asked to open an incoming text message, and then they will compare the 5 words displayed in the text message with those displayed in the secure messaging application, and confirm if the all words matched, and reject if any of them were felt to be mismatching. In the verbal condition on the right-hand side, the participant will be presented with an incoming phone call, which they will be, when clicking on, the 5 words will be read out. The incoming phone call was implemented using a text-to-speech application, using a pre-recorded sound clip. Now, in terms of our results, we decided to use non-parametric analysis since the data did not meet the requirements for parametric analysis. We reported medians and semi-quartile range as measures of central tendency and spread. For statistical testing, we use Wilcoxon-related samples tests to compare the pursuing conditions, and we also use Kruskal-Wallis tests to compare between different participants' information styles. Now, in terms of performance, the time to make correct comparisons did not differ significantly between comparison modes, with the summary statistics and test statistics shown in Table 4, and so hypothesis 1 was not supported. In terms of errors, so in general, participants did not make many errors. I think I've included the figures here, as figure 4 shows the number of errors made in the attack cases in the visual and verbal conditions, and really I think this just shows that there were not many errors, and that was in part due to the design of the attack conditions, which I will mention in the future slide. In terms of figure 3, though, there does seem to be an interesting difference between the number of errors made on non-attack conditions between the visual and verbal condition, with potentially the participants making a higher number of errors in the verbal condition. And in fact, this was a significant difference. Participants did make significantly more non-attack errors when using a verbal comparison, with the summary statistics and test statistics shown in Table 5. These results do support hypothesis 2 for the non-attack comparisons. In terms of perceived usability, the ratings on each dimension were highly correlated, with Spearman's row coefficients between 0.31 and 0.82, all with p less than 0.01. So we reported mean scores for each dimension. Now, of the 6 dimensions, there was interesting results on 3 of those dimensions. On the ease of use dimension, there was an effect that tended towards significance, with the verbal condition found to be easier to use than the visual condition. On the low mental workload condition, there was a significant result, again, with the verbal condition found to require lower mental workload than the visual condition. In contrast, on the confidence condition, though the summary statistics means are identical, there was an underlying difference in the data that was significant, with the visual condition perceived to provide increased confidence than the verbal condition. So this does provide partial support for hypothesis 3, but it does demonstrate a complex picture, where in some cases the verbal condition was optimal, and in some cases the visual condition was perceived to be optimal. Now, in terms of the effective information style, we found our sample was skewed towards users with a visual preference, which did affect our analysis. Participants were divided into roughly 3 groups. We had a verbal group of 18 participants who took scores between -9 and -1. We did not observe any participants who chose the verbal option for all 11 questions. The visual group consisted of 21 participants with scores between 1 and 5, and the very visual group consisted of 23 participants with scores between 7 and 11. In terms of results, we did not find a difference in correct comparison times between groups. And we also did not observe any difference in the number of errors on attack comparisons between the groups. We did notice that all groups made significantly more non-attack errors in the verbal condition, with the test statistics shown on the slide. However, this does not actually support hypothesis 4, as our prediction was that verbal users would make more errors in the visual condition, where in fact, verbal users actually made more errors in the verbal condition. So in terms of discussion, participants made less non-attack errors using a visual comparison mode. So one explanation for this is that it is easier to mishear than misread a word, especially if comparing unfamiliar words, as is often the case in the trust words wordless, as using strategic privacy. The visual condition was also perceived to provide increased confidence. In contrast, verbal conditions are perceived to be easier to use and require less mental effort. So in some cases, even though the visual condition may be perceived to provide increased confidence and performance, participant may just choose to use the verbal condition because it's just easier to use, and sometimes this is always a secondary task to actual communication. Furthermore, the lack of effect between comparison mode and information style was surprising. One explanation is that the main effect dominates, but this is we've got to be careful with using this conclusion as a sample is skewed. What I think is actually going on in the data is that the ILS may not be the correct measure of the underlying phenomenon. After in post-analysis, we noticed that 7 of the 11 questions actually provide 2 visual options rather than an auditory and visual option. We did notice in the data that there were examples of participants who performed better on the verbal condition than the visual condition, and vice versa, and also examples of participants who performed well in both conditions. But this performance was not correlated with their ILS score. Now, in terms of limitations, in addition to the limitation of the ILS visual verbal subscale, each condition only included 2 attacks, which was a flaw effect in our study. There was good reason for choosing such a low attack rate, as we did not want to expose participants to a high number of attacks, which would increase their awareness. But this needs to be addressed in future studies. Also, attacks lack sufficient similarity, and participants were able to easily identify them with ease. Again, which we will seek to address in future work. Further aspects of future work, we will attempt to identify a measure of difference between auditory and visual preference of participants. So one option at the moment is the VART questionnaire, which measures learning style differences between a visual, auditory, read-write, and kinesthetic dimension. We will be particularly interested there in differences between on the auditory and read-write dimensions. We'll also seek to investigate whether the effect persists using alternative fingerprint representations, such as a numerical representation as used in WhatsApp. The intention there is to see if the observed effect is specific to the trustworthy word list or more fundamental of a key fingerprint verification. We may also seek to include a toggle function so that we can ask participants to interact with a more realistic fingerprint comparison, as they are unlikely to be able to compare fingerprints with 2 devices displayed side by side, and much more likely to have to toggle between 2 screens displayed on a single device. So in conclusion, the optimal comparison mode remains unclear. It seems that some users may benefit given the option to compare fingerprints visually, but at the moment that is not supported by or encouraged by modern end-to-end secure messaging applications. The problem is complex and requires further investigation. Thank you for attending and listening to the talk. I'm happy to take questions.